So let us try to formally define this notion of abstraction refinement, right. So abstract interpretation or indeed abstract model checking, right, is dependent on the choice of the abstract domain, right. So there are different abstract domains with varying degrees of precision. Okay. So when we say that one abstract domain is more precise than other abstract domain, what do we really mean by that? Right? So let's try to define that more formally using the notion of abstraction refinement. Okay. So if you are given two abstract domains, let's say D1 and D2, right, and associated with that the partial orders and the concretization and abstraction functions. So we say that D2 refines D1, right, meaning that D2 is more precise than D1, right. So when we say D2 refines D1, that means D2 is more precise than D1. So we say that if for all sets of concrete states, right, so for all C which is in power set of states, so C is a set of concrete program states, gamma 2 of alpha 2 of C is a subset of gamma 1 of alpha 1 of C. Right. So what this essentially means is that if you have a set of states C, right, so I know that if I take its abstraction, right, meaning if I take the abstraction alpha 1 and if I take the abstraction alpha 2 of C, right, so this is the abstract value, right, corresponding to the set of program state C in both the domains, right, D1 and D2 respectively. Right. So now which domain is introducing less abstraction, right, or which domain is introducing less over approximation, right. So the over approximation is given by you concretize it back, right. So you concretize that abstract value back. So gamma 1 of alpha 1 of C is going to be another set of program states, right, and we know that C is going to be a subset of gamma 1 of alpha 1 of C, and similarly C is also going to be a subset of gamma 2 of alpha 2 of C, right, because when you abstract something and you concretize it back, you are introducing some over approximation, right. So now by saying that gamma 2 of alpha 2 of C is a subset of gamma 1 of alpha 1 of C, right, what we mean is that the domain D2 introduces less over approximation as compared to the domain D1, right, in the sense that every element that is there in the domain D2, right, every element in gamma 2 of alpha 2 of C is also present in gamma 1 of alpha 1 of C, but gamma 1 of alpha 1 of C may contain more states. So intuitively this D2 introduces less over approximation during abstraction, leading to more refined abstractions. Okay. So in order to illustrate this, right, what we just saw, right, so we have seen two different abstract domains. One is using the predicate set P1 and the other is using the predicate set P2. Okay. So so we said, right, so let's say this is the domain D1, right, which is the power set of P1 union bot, right, and this is the domain D2 which is the power set of P2 union bot. Okay. So what I claim is that D2 it refines D1, right, meaning that D2 is more precise than D1, right, and the way to see it, right, I mean we have seen by applying abstract model checking, right, that in fact D2 gives more precise results, right, in the sense that using D1 we were incorrectly showing that this program is actually not safe, right, but using D2 we were able to show that the program is safe, right, and indeed, right, so if you take a concrete program state, right, so let's take this particular concrete state C. Okay, so this is the state that you will get at the location L3, right. So if you execute the program, right, and if you reach the location L3, then you know that at the location L3 the value of lock is going to be 0 and the value of new is going to be old plus 1, right. That is because you would have already set old to new and then incremented new, right. So therefore new must be old plus 1, right. So now remember this is a set of concrete program states, right, because new is equal to old plus 1, there are many such pairs, right, of new and old, right. So for example old could be 1, right, and new could be 2, right, or old could be 2 and new could be 3 and so on, right. So this is a formula which is in fact encoding a set of concrete program states, right. So now if you take if you consider gamma 2 of alpha 2 of C and gamma 1 of alpha 1 of C, right, so let's calculate this, right. So what is going to be alpha 1 of C? So alpha 1 of C, right, is going to be you take the set of predicates from P1 which are satisfied by every state in C. Okay. So every state in C is going to satisfy lock is equal to 0. So therefore alpha 1 of C is simply going to be equal to P1. Okay. But what is going to be alpha 2 of C? So alpha 2 of C will be again the set of predicates that are satisfied by C, but in the set P2. Okay. So in the set P2 I have lock is equal to 0 which is P0, and I also have new is not equal to old, right, which is P3. So both P2 both P0 and P3 are satisfied by all states encoded by this concrete state C, right, this concrete element C. Okay. So this is alpha 1 of C and alpha 2 of C. Now what is gamma 2 of alpha 2 of C, right, and gamma 1 of alpha 1 of C, right? In particular, what is the relationship between these two sets? Okay. So gamma 2 of alpha 2 of C, right? So this is going to be the set of all program states which satisfy both P0 and P3, right? Meaning that the value of lock is 0, but the values of the variable new and old, they are not equal, right? On the other hand, gamma 1 of alpha 1 of C is going to be the set of all program states which satisfy just P0, right, here, which is lock is equal to 0. Okay. So now so this is only constraining the value of the variable lock, right? It is not constraining the value of new and old, right? Meaning that in gamma 1 of alpha 1 of C, I can have a program state which assigns the same value to new and old as well as different values to new and old, right? While in any state in gamma 2 of alpha 2 of C, the value of new and old is constrained to be unequal, right? Because alpha 2 of C contains the predicate P3, which is saying that new is not equal to old. So therefore, any state which is in gamma 2 of alpha 2 of C is also present in gamma 1 of alpha 1 of C, but the reverse is not true, right? Because there are states in gamma 1 of alpha 1 of C where the values of new and old are actually equal, but those states are not present in gamma 2 of alpha 2 of C, right? So therefore, gamma 2 of alpha 2 of C is actually a subset of gamma 1 of alpha 1 of C, right? And hence this is an example of abstraction refinement, right? So I have this particular concrete state C. So this is not true just for C, but it is also true for every possible C, right? So the definition of abstraction refinement says that for all C, right, for every possible set of program states, gamma 2 of alpha 2 of C must be a subset of gamma 1 of alpha 1 of C. So as a homework, right, you can do this exercise. So here we have shown abstraction refinement for a specific example of P1 and P2, right, but this is true in general, right, that if you are given sets of predicates P1 and P2 such that P1 is a subset of P2, then you can prove that the abstract domain, the predicate abstraction domain, right, that is parameterized by P2, which is power set of P2 union bot, it refines the predicate abstraction domain that is parameterized by P1, right, meaning power set of P1 union bot. So for this you will have to show the definition of abstraction refinement. Okay, so now the question is when abstract model checking, right, returns an error, right, in the sense that when it says okay, this program is unsafe, it returns a concrete counterexample, right, which is a set, which is a path, right, through the program. How do we then refine the predicate abstraction domain, right? How do we make it more precise so that this spurious counterexample goes away? So let us see how to find refinements of the predicate abstraction domain in an automated fashion, right? So we don't want to do this manually. So if verification fails with some set of predicates P, right, meaning that you apply abstract model checking with some predicate abstraction domain that is parameterized by the set P, right, and suppose the abstract model checking algorithm returns a counterexample which is a path from the initial location to the error location. Okay. So the first thing to do is to check whether or not this counterexample is valid or spurious. So the program may actually be unsafe, right. So how to check whether the counterexample is valid or spurious? So here this is a finite path, right, in the sense that this particular execution is going to consist of a finite number of transitions, right, and therefore you can actually execute the program along that particular path, right. So you can execute either concretely or you can execute symbolically, right. So you either execute the path concretely or you execute symbolically. How to execute symbolically we will just see now in the next slide, okay. But essentially by either executing the path concretely or symbolically, you will be able to infer whether this counterexample is valid or is it spurious. So if it is valid, of course the program is unsafe, but if it is spurious, then how do we know, right, that the program is safe or unsafe? So what we need to do is we need to refine the abstraction domain so that the spurious counterexample goes away, right, so which will make the counterexample infeasible. So let us see how to do that using this notion of a trace formula, and as it happens, right, this trace formula is also one way to symbolically execute a path in the program, okay. So what is the meaning of a trace formula? So suppose I am given this counterexample, right, so this counterexample I have indicated through this sequence of locations, right, so Li0, Li1 up to Lin, right. So where I0 is going to be the 0th location, right, meaning L0, and In is going to be the error location in the program, right. And along with that I am also assuming that each of these locations, right, I mean they are all going to be adjacent to each other, there are going to be transitions between these locations, right, because this is a path, and this transition is labeled by the command, right. So visually, right, I mean I have something like this, right. So from li0 I have an edge to li1 and then an edge to li2 and so on, right, up from n, then I have lin minus 1 up to lin, and this path is going to be labeled by the commands, right. So the commands I am denoting using the cij plus 1, right, meaning that this command is going to be ci1, this command is going to be ci2, this command is going to be ci3, and this command is going to be cin. Okay. So these are the commands that are labeling the edges along the path. Okay. So what we will do is we are going to symbolically execute this path by constructing its trace formula, and to construct the trace formula we are going to use the first order logic encoding, right, of each of these commands, right. So for all of these commands, right, we know that there is this first order logic encoding which is given by rho of ci, okay, ci, let us say k. Okay. So the rho of cik, right, gives the first order logic encoding, right, and this first order logic encoding, as we have seen earlier, right, this is over two variables, right. So this is over sets of two variables, the primed variables and the unprimed variables, right, where the primed variables corresponding to the program state before executing the command, the unprimed variables, right, correspond to the program state before executing the command, and the primed variables correspond to the program state after executing the command. Okay. So what we are going to do is we are going to simply conjunct, right, all of these FOL encodings, right, of the corresponding program statements by and also substitute these variables appropriately, right, so that the state, right, the program state that is obtained before, let us say, some command, right. So if you take this command cik, right, so the program state that is obtained before and after, right, so the before, right, this will be given by the program state that is obtained after executing cik minus 1, and after executing cik, right, the program state is going to be fed to cik plus 1, right. So this is how we are going to rename the program state. So let us look at the trace formula. So this is going to be the trace formula, right. So it is just a conjunction of all the FOL encodings of all the commands with appropriate renaming of the variables, right. So the variables are renamed in such a way that vj replaces v while vj plus 1 replaces v prime, right, where what is this vj and vj plus 1, right. So vj is nothing but all of the program variables with the suffix j attached to them, right. So if let us say your program variables are something like x, y and z, right, then this vj is going to be something like xj, yj and zj. Similarly this vj plus 1, right, this is going to be xj plus 1, yj plus 1 and zj plus 1. So what we are essentially doing is we are substituting vj for the unprimed variables and vj plus 1 for the prime variables, right, meaning that vj is the program state before executing cij plus 1 and vj plus 1 is the program state after executing cij plus 1, right. So again, if you try to visualize what is happening, right, so for the program command c1, rather ci1, right, so this row of ci1 here v0, right, is going to replace v, and v1 is going to replace v prime, right, and then this will be conjuncted with so ci2, right, where v1 is going to replace v and v2 is going to replace v prime and so on. So you can see that v0 is the start program state, right, and v1 is the end program state after executing ci1, or right. So now remember ci1 is the edge, right, from li0 to li1, right. So this is ci1 and then this is ci2, which is the program command from li1 to li2, right. So v1 is then the start program state of the command row of the command ci2, right, meaning that we have fed the end program state from ci1 to the start program state of ci2, right, and so on. So we will keep on doing that, right, and at the end we will have vn plus 1, right, which will be the end program state, right, which is the program state obtained after executing all the commands in the path. Okay. So this is the trace formula. So given this path, right, you can automatically construct this trace formula, right, because all you need is the FOL encoding of each of the individual program statements, the primitive program statements. Remember that only primitive program statements are present on the edges of the path, okay, and all of the for all of the primitive program commands in the imp language we have already defined their FOL encoding, right. So this trace formula can be automatically constructed. So rho of Cij is the encoding of the operational semantics of Cij in FOL. So let us take an example, right. So here using this particular predicate abstraction domain P, right, applied on this example, right, we had actually got this counter example along the paths L0, L1, L2, L3, L4, L5 and L error. Okay. So here is the trace formula, right, of this particular path, right. So I have slightly cheated here in the sense that if you consider row of, for example, the first statement, right, which is this assignment statement lock equal to 0, right. So you will have something like lock prime equal to 1, right, and you will also have old prime equal to old and new prime equal to new, right, because old and new are the other program variables, right, for this particular program. And the assignment, the FOR encoding of the assignment statement has something like frame lock, right. So frame lock meaning that the values of the other variables don't change. Okay. So every time you will essentially assign new indices to old and new, right, in fact to all of the three variables even though their values are not changing, right. So I have not considered something like this old prime equal to old and new prime equal to new, right. Instead, only when there is an assignment statement to that particular variable, right, I have introduced a new index, right. I have essentially introduced a new version of that variable, right. So for example, for this command there is an assignment statement to lock, right. So therefore I have added lock1 equal to 0. Next, from the L1 to L2 command, right. So here there is another assignment statement to lock, so therefore I have added another version of the lock variable, right, which is lock2 is equal to 1. While here there is an assignment to old, right. So therefore I have added old1 equal to new 0, right. So new 0 is the original version of the variable new, while old1 is the new version of the variable new, meaning it's the value of the variable old after executing this particular program statement, right. So similarly I have lock3 equal to 0 and new 1 equal to new 0 plus 1, that is the FOR encoding for the program statement from L2 to L3, right. So again it's a new assignment to lock and a new assignment to new variable, right. So then from L3 to L5, L3 to L4 I have just skip, right, and then from P0 from L4 to L5 I have this assume new equal to old. So this is not an assignment statement, right. So this has to reuse the values of new and old that were assigned originally, right, that were assigned before the statement, right. So before this statement is executed, I have this assignment of old and this assignment of new, right, which is old one and new one. So that's why I'm using that version, right. New one is equal to old one, and then I have this assume lock equal to 0 from L5 to L error, for which again I am using the most recent assignment to lock, right, which is lock3. So that's why I'm using lock3. So lock3 is equal to 0. Right. So this is the trace formula for this particular path, right. And what you can notice is that this trace formula is actually unsatisfiable. So if you give this trace formula to any SAT solver, right, will say that this is unsatisfiable modulo, of course, the theory of integers and so on, right. And the reason it is unsatisfiable is because of this old and new, right. So I have old one is equal to new 0 and new one is also equal to new 0, right. New one is equal to new 0 plus 1, right. So old one is new 0, new one is new 0 plus 1, but then we are also saying new one is equal to old one, right. So that is not possible modulo the theory of integers, right, because you are adding 1 to new 0 here, while here you are not doing anything, right. So old one cannot be equal to new one, right? And so that's why this formula is unset. So if the formula is unset, meaning that this particular path is infeasible, meaning that the counter example is spurious. Okay, so now once you have a spurious counter example, right, meaning you construct the trace formula, right, and you have found a spurious counter example, now I need to refine the abstract domain, meaning find new predicates, right, so that this spurious counter example goes away, right. So we will see an automated procedure to even find new predicates, right, which is called interpolation, right. So interpolation is a technique which is used for finding new predicates in the predicate abstraction domain, right. So given an infeasible, so what are we given so far, right. So when will interpolation be applied, right. So we have already applied abstract model checking with some predicate abstraction domain, right, with some set of predicates, and I have got a spurious counter example which is given by an unsatisfiable trace formula, right. So essentially I have a formula which is unsatisfiable. So that is what we are going to start from, right. So we are going to assume that there is a trace formula and the trace formula is unsatisfiable. So what is this notion of interpolation, right. So suppose I have let's first define interpolation, right, in a generic fashion. So interpolation is a concept from first order logic theory. Okay. So what does it say? So it says that if I have formulas A and B such that A and B is unsatisfiable, so A and B are some arbitrary formulas, but all I know is that their conjunction is unsatisfiable. Right? Then what is an interpolant? So, interpolant I between A and B is another formula such that it satisfies certain constraints. Right? So, it satisfies 3 constraints. So, this I is the interpolant, right, between A and B. So, this is a formula and it should satisfy these 3 constraints, right. The first constraint says that A should imply I, right, meaning that A implies I is valid. Okay. The second constraint says that I and B is unsatisfiable. Okay. And the third constraint says that variables of I must be a subset of variables of A intersection variables of B. Right. So, what is this vars of I? So, this vars of any formula F, right, these are the free variables in F. So, free variables in F meaning all those variables which are not bound. Okay. So, what this last constraint is saying is that if you take the free variables in I, then they must be free in both A and B. Right. So, because it's a subset of the intersection of vars A and vars B. Right. So, any free variable in I must have been free in both A and B. Okay. So, let us take an example to make this more clear. So, let us take these two formulas A and B. Okay. So, A is saying x is greater than 0 and x is equal to y and y prime is equal to y plus 1, okay, while B is saying that y prime is less than 0. Okay. So, first of all, what are the free variables, right, in A and B, and then what is the intersection, right. So, x, y and y prime, these all are free, right. So, this is vars of A. So, they are all free in A, while vars of B only contains y prime. So, y prime is the only variable that is free in B. Right. So, now vars of I must be a subset of vars of A intersection vars of B, right. So, the intersection of both these sets is just y prime, which means that the interpolant can only contain the variable I prime, can only contain the variable y prime, right. And it also has to satisfy these two constraints, right. So, meaning that A should imply I, right, and I and B should be unsatisfiable. So, if you stare at these two formulas, right, first of all convince yourselves that A and B is actually unsatisfiable. Right. So, you can see that if x is greater than 0, right, and x is the same as y and y prime is y plus 1, what does that say about y prime? Right. So, because x is greater than 0 and you are adding something to y, but y is the same as x, right. So, therefore, y prime must also be greater than 0, and then B is saying y prime is less than 0, right. So, therefore, A and B is clearly unsatisfiable. Now, what is an interpolant here? Right. So, an interpolant is something that should only contain the variable y prime and it should also satisfy these two constraints, right, meaning that A should imply I and B should be unsatisfiable. So, in this example, one clear interpolant, right, is y prime is greater than 0. So, you should convince yourselves that A in this case does imply I, right, because as we just discussed, right. So, since y prime is equal to y plus 1 and y is the same as x and x is greater than 0, therefore, y prime must also be greater than 0, right, and y prime, right, I and B is clearly unsatisfiable, right, and furthermore, the I only contains the free variable y prime, right, which is free in both A and B, right. So, therefore, I is an interpolant of A and B. So, here is a very important result from first order logic theory, right, which is the Craig interpolation lemma, which says that an interpolant always exists, right. So, given formulas A and B such that A and B is unsatisfiable, right, an interpolant I can always be constructed, right. So, there always exists an interpolant I which will satisfy these three properties, right. So, now we are going to take advantage of this interpolant, right, and we are going to use this interpolant in order to get more predicates for the predicate abstraction domain. Okay. So, the proof of Craig interpolation lemma, right, it essentially automatically constructs this interpolant from the proof of unsatisfiability of A and B, right. So, we are not going to go through the proof of this lemma, but that is how it works. Okay. So, now what are we going to do? So, in order to apply the theory of interpolation, we need an unsatisfiable formula, and we already have an unsatisfiable formula, which is the trace formula, right. So, what we are going to do is we are going to take a look at this trace formula. So, this trace formula is a single formula. So, we are going to partition it into two formulas A and B, right, such that since I know that the entire trace formula is unsatisfiable, so A and B is clearly unsatisfiable, right, and then we are going to see what will be the interpolant of A and B. So let us take our running example, right. So in this example we have constructed this trace formula and we have already seen that this trace formula is actually unsatisfiable. Right. So let me partition this trace formula into A and B as shown, right, by the red and the green lines, right. So the red line is the formula A and the green line, right, is the formula B. Okay. So again the entire formula is unsatisfiable, therefore A and B is clearly unsatisfiable. What will be the interpolant of A and B, right. So the interpolant first of all should contain variables which are free in both A and B. So if you again take a look at these two formulas, right. So log 3 is used in both formulas, right, therefore it is free in both, but otherwise, right. So what else is used? So old one and new one, right, they are used in A and they are also used in B, right. On the other hand, log 1, log 2 and new 0, right, they are not used in B, right, and therefore they cannot be part of the interpolant, right. So the interpolant can only contain the variables log 3, new 1 and old 1. Okay. Now in this case what is the property, right. So what is the interpolant I, right, such that I and B will be unsatisfiable but A will imply I. Okay. So this I, since it contains only new 1 and old 1, right, again, right, you can kind of try to work it out on your own, right, and you will see that a valid interpolant in this case is something like new 1 is not equal to old 1, right. So this is a valid interpolant because A implies I, right. So because new 1 is new 0 plus 1 and old 1 is new 0, therefore new 1 is clearly not equal to old 1, and not only that but I and B is also unsatisfiable, right, because I is saying new 1 is not equal to old 1 while B is saying new 1 is equal to old 1, right. So therefore I is actually a valid interpolant for this A and B. Okay. So this is one valid interpolant which is old 1 not equal to new 1. Let us consider another partitioning of the trace formula. Let us suppose I partition the trace formula in this fashion. Okay. So now the size of the formula A has decreased, but the size of formula B has increased. Okay. So again this A and B is unsatisfiable because the entire trace formula is unsatisfiable. So again I try to ask, okay, what variables can be present in the interpolant. So remember, an interpolant always exists, right? So no matter how I partition this trace formula, an interpolant will always exist. So in this case again I look for the common variables. So I see that old 1 is being used in both, right, and new 0 is also used in both, right, but log 1 and log 2, right, they are not used in the formula B, right? And similarly new 1 is not used in the formula A and log 3 is also not used in the formula A, right. So therefore my only possible choices, right, are over old 1 and new 0, right. So these are the only variables that can be free in the interpolant. Right, and again you can try to work this out, right. The only interpolant here, right, is simply going to be old 1 is equal to new 0. Okay. So this will be a valid interpolant because A does imply I, right, and I and B is going to be unsatisfiable, right. So in fact this old 1 equal to new 0 is essentially the crux of unsatisfiability, right. So this is the reason why A and B is unsatisfiable. Okay. So because if old 1 is equal to new 0 and new 1 is equal to new 0 plus 1, then new 1 will not be equal to old 1, right. So therefore here a valid interpolant is old 1 is equal to new 0. Okay. So you can see that earlier, right, in the previous partitioning, right, we had got something like old not equal to new, while here we have got old is equal to new, right. So I am ignoring the suffixes for now, right, the versions of the variables, right. So again if you recall, right, when we had went through this example, right, with the new predicate abstraction domain, these are the exact two predicates that we had added, right. So we had added old 1 equal to new 1, or rather old not equal to new and old equal to new, right, into our predicate abstraction domain, right. So from P1 we had gone to this predicate abstraction domain P2, right, which included these two new predicates, and with the help of these two predicates, right, you would be able to show that this program is actually safe, right, in the sense that this error state is not reachable. Right. So this is not a happy accident, right. So in fact this is guaranteed to happen, right, in the sense that if you have a trace formula, right, so what we are going to do is, given a trace formula which is unsatisfiable, we are going to consider every possible partitioning of this trace formula into A and B, right. So if you have a trace formula, right, which is, let's say which consists of n commands, right, there are going to be total n plus 1 different partitionings of the trace formula, right. And what we are going to show is that for each of those partitionings of the trace formula, right. So this is one possible partitioning, right. So we are going to consider every possible partitioning of trace formula, and for every partitioning we are going to find, okay, what is the interpolant. So what we will get is a chain of interpolants, right. So this interpolant ij, right. So in this case, if you partition this trace formula, so this is going to be the general form of the trace formula, right. So it's going to be a conjunction of the F4 encodings of all the commands, right. So this interpolant ij, right, this is so this corresponds to this partitioning where the formula A, right, stops at row ij and the formula B begins at row Cij plus 1. Okay. So what is the property of this interpolant ij? Okay. So this interpolant ij essentially contains the states which are reachable after j steps, right. So remember that this A must imply I, right, and this A, right, in this case is the FOL encoding of the commands from Ci plus Ci1 to Cij, right, meaning that these are all the program states which are possible after the first j steps are executed, right. So these are states which are reachable after j steps, but they cannot complete the remaining steps, right, because I know that the entire formula is unsatisfiable, right. So I and the rest of the formula B is unsat, right. So these are a set of program states which are reachable after j steps, but they cannot complete all the remaining n steps. Okay, and all the variables of this formula are going to be in Vj, right. So this is the most crucial step, right, and this is where we really need this property, right, that the free variables in the interpolant must be in the intersection of the free variables, right. So if you take these two formulas, right, so this is A and this is B, what are the common variables in this formula, right. So you will notice that the only common variables are going to be Vj, right, because Vj, right, this is going to be the output of the Cij and this is going to be the input to Cij plus 1, right. All other variables, right, so we are going to use variables such as V0, right, V1, V2 and so on, right, and here we are going to use variables Vj plus 1, Vj plus 2 and so on up to Vn plus 1, right, but Vj, right, this so these are the Vj variables, right, these are the only common variables between these two formulas, okay. And therefore an interpolant must have all variables in Vj, right. So what we have accomplished through this, right, is that I know that all variables in Vj, right, essentially correspond to the state after executing the first j steps, right. So we are not mixing together versions corresponding to different program steps, right. So our interpolant only contains all the variable versions which are reachable after a fixed number of steps, right, which is after j steps. So as I mentioned, right, so our goal is to essentially consider every possible partitioning, right. So for every partitioning we will get a new interpolant. So what we will compute is a chain of interpolants, right, I1 up to In minus 1, right, and it so happens that this interpolants, the reason they are called a chain, right, is because they will also satisfy this inductiveness condition, right, meaning that Ij and row Cij plus 1 will imply Ij plus 1, right. So this is a formula, this formula is going to be valid, okay. So from this interpolant chain, right, we are going to obtain new predicates by removing the subscripts from the variable names, right. So essentially we are just going to ignore all the subscripts to the variable names, right, we are going to ignore which versions the variable correspond to, and we are going to simply after removing the subscripts, right, whatever formulas we get, they will be the new predicates which will be added to the predicate abstraction domain to refine it, okay. And here is another important guarantee, right, which is that if you add all interpolants from the chain, then this is guaranteed to remove the spurious counterexample, right. So meaning that if you add all the interpolants, right, that are computed using this interpolant chain, so if you add all of them to the predicate abstraction domain and then rerun the abstract model checking algorithm, it is guaranteed that the spurious counterexample that you received, right, corresponding to this particular trace is going to be eliminated, right, in the sense that abstract model checking is not going to revisit this same spurious counterexample, right. So again this is a guarantee, okay.